So I am traveling in LA right now, and I brought my radiation detector with me, as one usually does when they travel. So I came over to the granite counter here next to the bathroom and noticed that my radiation detector was reading actually a lot higher than normal. You can see here, this is a typical background, around 8 or usually less micro R per hour, but when I put it on the granite here, and there it goes, starts going up and up. And look at that, it went up a lot higher here. And that's typically because granite has naturally occurring radioactive material in it, and it is actually usually uranium. So I'm going to do a quick analysis just to show what type of isotopes we're dealing with. So now we're looking at what's called a gamma spectra, and you might not have known that a radiation detector tells you more than, say, just the radiation levels. It actually can tell you what sort of isotopes are you looking at, what specific type of radioactive material, and that's by using this gamma spectrum. And in this gamma spectrum, you can see at the bottom there it says 4, and then it goes up in certain increments all the way up to 2763. That's in energy of the gammas, in kilo electron volts. It's just a unit of energy. What happens is a photon, in the form of, say, a gamma ray or an X-ray, will interact with that little black detector. There's a crystal in there, and it'll create a pulse in that detector. And the larger the pulse, the higher it thinks that photon is, or gamma is, and it will count it in these. You can see those spikes. That's every single count. It kind of piles up like a Connect 4 game. It'll pile it up at that higher energy. So say this spike right here, this is actually corresponds to, you can see at the upper left hand corner it says K40. That's potassium 40. It's a naturally occurring radioisotope out there. It sees that in the background, and you can see it's piling up in this range here due to counting those gammas. And I'm going to go ahead and let this sit for a little while longer so I can get a clear picture of what exactly the isotopes we're seeing besides just potassium 40. All right, so it's been over an hour of collecting data here. It's a low dose rate, so you have to collect for a while, but you can see it looks still pretty noisy up here. It's gotten better down here. You can see as it starts like getting more confident with its answer, it starts changing this orange color. But one of the things you can do is this filter on this on the bottom here. You can adjust it. You can see without the filter at all, it's extremely noisy. But then you start adjusting the filter, and what it does is it kind of makes those peaks a little more prominent, I would say. But it does also kind of make up some peaks as well. So I try not to overdo it on that. But let's go ahead and adjust it there. And if you drag your finger on the screen, you can line yourself up with these different peaks. There's that potassium 41 again. And then let's see. Let's line it up with this one here. So you can see where it's purple. That's where my finger is. I can line it up with one of these peaks, and you see there's a bunch of red ones that pop up. And what it does is it can pull up the different associated gammas for different isotopes out there. So let's see, this one right here, lead 212, and you can see all the red lines that line up with all sorts of other peaks on here. Let's look for another one, bismuth 214. That's another likely culprit, and you can see there's a lot of peaks that line up. And let's go ahead and see, why would you see bismuth 214 or maybe lead 212? Well, let's go ahead and look at the chart of the nuclides. Figure out why I'm seeing bismuth 214, I'm pulling open this thing called the chart of the nuclides. You've probably seen the periodic table of elements. This is like that, but like on steroids. You can see all the elements there, and there's a lot more to all of the different isotopes than just the periodic table of elements. This shows you the different isotopes that make up a lot of these elements. And if you zoom in here, remember we saw Bismuth 214. And if you click in here, you can actually see all of those gamma peaks that we saw, all those energy lines that were showing up red when I hovered over some of the energy lines. And another thing you'll notice here is Bismuth 214 actually has a fairly short half-life. So you might wonder why this granite that is actually extremely old would have something with such a short half-life. Well, that has to do with what's called a decay chain. And you can see here, it kind of shows it a little bit. The parents, it has actually a parent. And if you go back to the chart of nuclides and you press on Bismuth 214, it shows you some of those isotopes that can actually decay into Bismuth 214. And that would be lead 214. And if you keep tracing it back, you have to kind of know how to trace it back, but I know exactly what the answer is. It comes from polonium 218, which comes from your radon, which this is the radon that people talk about when it comes to build up inside your homes, radon 222. And then from there, before that, it was actually radium. That when you hear about like radium dials or radium dial girls, this is that radium. Then you have your thorium and actinium. Actually, no, not actinium, sorry. Uranium 234, which comes from protactinium 234, thorium 234, and the one that it actually all comes from is uranium 238. And if you press and hold on that, it shows you that exact decay chain that I just showed you. And that's how you get the lead 214 and the bismuth 214, which we saw the bismuth 214 in those energy lines. And even though these are actually all pretty short-lived, see 20 minutes, 30 minutes, 3, radon itself is only in days. If you keep going back, like radium, that has a much longer half-life. That'll stay around for a long time. So that's built up in that granite, and which, because it's in there, all these other isotopes are also built up in there. And not only radium is in granite, but I know for a fact that uranium also is in granite. So if you have a lot of uranium in there and it's decaying to all these other isotopes, all of these other isotopes just build up in the granite, and that's why we see bismuth 214, and it's the reason why I can take a detector up to it and you can see that it is in fact radioactive.